Dear ECTC 2020 attendees, we would like to welcome you to session number 3 titled Antenna in Package for 5G and Radar Systems. This session has been organized by the High Speed Wireless and Components Technical Committee of the ECTC conference. My name is Maciej Wojnowski from Infineon Technologies. My colleague and co-chair of this session is Hideki Sasaki from Renesas Electronics Corporation. This session has been sponsored by EMD Performance Materials. We have 7 papers in the session, 3 papers from industry and 4 papers from research institutes and academia. Our first talk will be given by Atom Watanabe from Georgia Institute of Technology. It will be followed by the talk of Renuka Bowortu from University of Florida. The third talk will be given by Ivan Deep from Fraunhofer Institute for Reliability and Microintegration. The talk number 4 will be presented by Maesam Malem from Texas Instruments, and the talk number 5 by Ricky Xie from ASE Group. The talk number 6 will be given by Shirong Li from Hitachi Chemical, and we will close the session with the talk number 7 by Quan Shi Woon from National Taiwan University. We believe you will find it extremely interesting to learn about the innovative developments in the area of antenna in package for communication and radar system, and enjoy the talks as much as we did. Thank you very much for attending.
Hello, I am Adam Watanabe, a PhD student at Georgia Tech. First of all, thank you for coming here and showing your interest in my paper. I have actually presented 5 papers as a PhD student at this conference ECTC, and I'm about to graduate, and this is going to be my last presentation at ECTC as a student. This time I will be talking about glass-based IC embedded antenna integrated packages for 28 GHz high-speed data communications. This work is conducted in conjunction with Georgia Tech Packaging Research Center, led by Professor Tumala and Professor Swaminathan. So here is the outline of my presentation today. I'm going to provide a high-level discussions first, starting from research objectives and a strategic need for AIP, and I'll quickly touch on some previous work followed by technical challenges, and then I'll show you our unique approach at Georgia Tech and following research tasks. Then I will be going into details of glass-based packages in the results section. Okay, let me quickly introduce the research objectives of this work. The main objective is to model, design, and demonstrate ultra-thin antenna integrated 3D glass-based millimeter wave modules on 100 to 300 micron thick glass substrates for 5G packages. There are a couple of key parameters in terms of performance and miniaturization. Regarding the performance, we'd like to get almost 2x signal routing density compared to the conventional RF packages, which leads to miniaturization of the entire package and mitigates the system interconnect loss. Another key metric is the antenna performance. Having realized gains higher than 3 dBi over the target frequency range is of significance. The key parameters to miniaturization are also listed over here. Dielectric film thickness for DL, the core thickness, and metal layer count are the important metrics we have to look at to miniaturize the entire antenna package. To meet the key parameters, we have 2 options. One is chip plus or flip chip structure. The other is chip first or chip embedding structure. I'm focusing on chip first in this presentation. Before diving into deep discussion on the research results, let me quickly introduce strategic need for 5G packages. The new architectures for 5G lead to the requirement for new class of substrate technologies. Those are 1. Package-level heterogeneous integration of active and passive components, filters, heat sinks, and antenna arrays. 2. Ultra-short low-loss interconnection lengths. 3. Advanced phased antenna array implementation. Actually, the most notable packages used for 5G millimeter waves are the modem module package and antenna integrated package. In such system on packages, we integrate, modem die, memory die, transceiver die, power module die, filters, antennas, discrete passive components like resistors or capacitors. And if you take a closer look at the trend in 5G antenna integrated packages, we can classify the trend into two packaging trends from the form factor standpoint. One is flip chip interconnect or chip last. This packaging method has been the mainstream in the industry because of the process maturity and supply chain readiness. However, if we look at the future trend, which is mainly driven by high-performance computing applications, chip embedding or chip-first packaging structure are coming next. Infineon and TSMC are leading this fan-out technology. Their packaging technique is technically based on a epoxy molding compound, which goes a bit against form factor challenge. So our idea is to do this chip embedding or fan-out packaging with a glass substrate. With this glass panel embedding antenna integrated package, we have an IC embedded antenna sitting on top with redistribution layers for signal and power distribution on double side of the package. This packaging structure addresses these technical challenges. The first set of technical challenges is low-loss high-density interconnect. We need to mitigate signal losses caused in package and also need to control impedance very well in this kind of analog domain. We also want to use thin dielectric films for package miniaturization and develop a process for chip embedding into a glass substrate. In terms of antenna design, we have to take care of bandwidth and efficiency/realized gain since we are trying to reduce the entire thickness. In addition, design of highly integrated module is another key to make such complicated module work. And here is our unique approach. I know lots of people still ask us why glass. So I made a radar chart explaining the key properties of major 3 substrate technologies. If you look at organic substrates, which are colored in red, we can still tell that the process maturity and supply chain readiness are obvious. However, glass substrate is showing a superiority in electrical and mechanical properties in addition to the metallization feasibility, thickness reduction, and dimensional stability. In order to enable heterogeneous integration or more dense signal routing, we have to go into the direction that high-performance computing is taking right now. Having said that, the dimensional stability of glass substrates shines over here. As I mentioned in the previous slide, IC embedding is essential for the next generation package for 5G millimeter waves. The advantage of glass over here is the capability to form double-side metallization. To demonstrate the chip-embedded glass-based antenna integrated packages, we worked on several research tasks. The first set is a process development, which includes glass cavity formation and also the placement of an MMIC die And also we laminated a low-loss dielectric polymer over the MMIC. The second part is the comparison of interconnection techniques. We compare the the electrical insertion loss and also impedance matching between flip chip and IC embedding interconnections. And the third part is the antenna integrated package design, which includes integration of active and passive components in the module. And also, I'll show you a couple of material impact on bandwidth and gain of antennas. And I'll show you the final antenna design and performance. So research results section have 3 parts. And I'm going to focus on the first part, process development. Okay, let me talk about the process flow that we developed. So we have a panel glass, which is 120 micron thick, and we drilled a glass cavity using a femtosecond laser, and we attached the thick 1.1 millimeter carrier glass from the bottom side using a thermal release film provided by Nitto Denko. And we mounted an MMIC, in this case it's an LNA, with the face down. And we laminated a low-loss polymer, which is Taiyo Zeristo, from the top side. And we also attached a thick glass carrier again. And we removed the bottom side of the glass carrier and laminated low-loss polymer, again Taiyo Zeristo, and removed the top side of the glass carrier. And we drilled micro vias for electrical connections, and RDL formation was stalled because of the COVID-19 situation. So we're going to resume this after a lab reopening. So let me show you some characterization results. So this is the these figures are the top views for a glass panel with the cavity drilled. So this is a Z profile of the cavity. So it had the thickness was 120 micron, and it had almost 75 micron taper, which is almost like a 60 degrees slope. And here is the figure of the MMIC and LNA embedded into the glass cavity with the low-loss film Taiyo Zeristo laminated over it. So, and also successfully we got a cross-section figure using a microscope. We can see that like a very flat surface with the low-loss polymer laminated over the glass substrate and also MMIC. As we were talking about process development, let me move on to the second part, which is comparison of interconnection techniques from the electrical standpoint. So here's the comparison from the electrical standpoint between the C4 bump interconnection, which is shown over here, and microvia interconnection or IC embedding that is shown over here. If we look at return loss as a function of frequency, with the microvia interconnection shows better return loss, while if you look at the insertion loss, again microvia interconnection shows lower loss. So the key takeaway messages from here are short interconnect connect lengths from microvia interconnect lead to lower loss, and also low loss dielectric. The use of low loss dielectric, as shown over here, contributes to the lower insertion loss because we need to elevate high DF solder resist for flip chip technology, and it is easier to get impedance continuity with microvias because we can control the microvia diameters and also pitch very well. So we try to embed an LNA from analog devices into the glass substrate that is shown over here. So this LNA has a pad size and pitch of 100 and 200 microns, and the cross section is shown over here. And this LNA is connected to coplanar waveguides that is sitting on top, and that is connected through micro-via interconnects. And if you look at the frequency response or S parameters, we can easily tell that we don't see much difference between the frequency response with micro-via interconnects and without micro-via interconnects, indicating that the micro-via interconnection does not degrade the LNA performance. This is quite important for RF or 5G millimeter wave packages, and also low loss system interconnect as well. Okay, now let me talk about the last part of the results section, antenna integrated package design. Okay, so this slide shows the antenna integrated module that consists of COTS LNA that is embedded into the glass substrate, and also surface mounted decoupling capacitors, and also 1x4 antenna array, which is aperture coupled patch antennas, and also bandpass filters that are sitting at the bottom again. And so the bandpass filter is a fifth order interdigital bandpass filter that is shown over here, and that covers the 25.5 gigahertz to 30.4 gigahertz, which is pretty good bandwidth. And also the size is really important for this kind of passive components in a package. And the more details are discussed in one of the papers, and this paper is written by one of the co-authors of this paper, Muhammad Ali. So here, let me focus on the antenna and show you some thickness dependence on bandwidth. So here's the one of the key parameters, which is D, the thickness or separation distance between the radiating patch and a parasitic patch. So the D is in the x-axis, and bandwidth is in the y-axis. If we increase the thickness of the separation, we can get higher bandwidth. This is a pretty well-known idea. If we increase the thickness of the substrate, we can get a higher bandwidth. But the key takeaway is we have to balance the trade-off between the thickness versus bandwidth. Of course, we can get a higher bandwidth with a thick substrate, but in order to miniaturize the antenna integrated package, we also have to sacrifice bandwidth to a certain extent. So let me show you another set of antenna study on DF dependence on antenna gain. So here is the radiating patch and the parasitic patch fit by aperture coupling. If you look at the antenna realized gain in the z-axis, which is defined by color, and I try to change the DF or loss tangent of dry film and glass, and if you use very low loss, actually very traditional FR4, which has DF of 0.02, the gain is pretty low. But if you use pretty low DF materials for both glass and dry film, we can get a very nice realized gain. So both dielectric losses affect the gain of the patch antenna a lot. So that's the main reason why we need low loss materials for antenna integrated packages. So let me show you the final antenna design. We chose to have 142 micron for the separation between the parasitic and radiating patches. Those are both squares, but they have like a 200 micron difference in terms of the size. And also we have a ground plane in M3 with a dumbbell shaped type of slots, and those patches are fed by microstrip lines. And this is the antenna performance. So the antenna consists of 1x4 antenna array, and they are 5.4 millimeter apart, and each element has 2.5 times 2.5 millimeters squared, with a realized gain of 6.3 dBi, as you can see over here, as a function of frequency. And the stack-up is balanced like on both sides of the glass substrate. And if you look at the bandwidth, which is pretty wide, it has more than 4 gigahertz. If you look at the realized gain, that is higher than 3 dBi, and also we got pretty good realized gain over the 40 degrees C. So let me quickly summarize my talk, which was about glass-based IC embedded antenna integrated package, starting from process development, which included a glass cavity formation, and also die placement and low-loss dielectric lamination. And also we showed you some electrical comparison of interconnection techniques between like flip chip and IC embedding. And finally, we presented an antenna integrated package design with some material impact of bandwidth and also antenna gain and efficiency. And future work includes multi-die implementation with integrated passive devices. And we are trying to apply this technology to 6G / sub-terahertz frequency bands. And we especially acknowledge Georgia Tech Packaging Research Center Consortium for their support. And these are the references. And thank you very much for your attention. If you have any questions, feel free to contact me. I'm very happy to take them.
Hi, this is Renuka Bhaurata from University of Florida, and I hope everyone is safe and healthy. Today I want to talk about 3D integrated through fused silica via-based array antenna for millimeter wave communications. The outline of my talk is going to be a brief introduction, previous literature, the goal of this work, and a few discussion points on design of 28 GHz array antenna, followed by the fabrication and different RF measurement techniques that we have been used, the comparison of this work with the previous existing array antenna designs, and I'm going to finally conclude my talk with conclusion, future work, and acknowledgement. As we all know that we started with mobile generation 1G, where everything is analog and the data rate is close to 2 kilobits per second. We try to digitalize the signal transmission and reception and also simultaneously increase the data rate in 2G communication. From which we jump to 3G, where we try to increase the bandwidth, and also we try to incorporate different multiplexing schemes like wideband, code division, multiple access, time division, synchronous multiple access, and also increasing the data rate compared to 2G. In 4G, we can see that the maximum data rate that we can achieve is close to 1 gigabits per second. So if we see our journey from 1G to 4G, one thing is for sure, we are trying to increase the data rate, and it is also estimated that by 2021, nearly 28 billion devices will be connected through IoT. So what is something new that we're going to expect in 5G? If you look into the frequency spectrum between 3 to 300 gigahertz, till now from 1G to 4G, all the devices like the smartwatch, phones, virtual reality, the smart lock, lamp, everything is occupied below sub 6 GHz. The above frequency range is nearly empty, except few frequencies like 60 GHz, which is used for satellite communications, and 77 GHz, which is used for anti-collision radar technologies. With 5G, we are trying to broaden this frequency spectrum where the devices occupy higher frequency ranges so that each device will have more bandwidth and less interference. So in 5G, we are going to have three frequency bands. One is sub 6 GHz, second frequency is between 28 to 38 GHz, and the third one is above 60 GHz. With this, the main advantages we are going to have is more data rate, more bandwidth, multiple frequency bands, and massive multiple input and multiple output antennas. So with 5G, we are trying to effectively use the frequency spectrum. But what are the challenges that we might face across this? If we look into the RF transceiver architecture here, we have different components like the antennas, filters, low noise amplifiers, power amplifiers, and voltage control oscillator. If you look into each and every device, for instance in the antenna, you have the substrate and the radiating elements and the power feeding to these radiating elements made of copper. Similarly, if you look into the transmission line, for instance, the coplanar waveguide feed line, you can see that you have the substrate and the copper traces which connects different components. If you look into the active components like the voltage control oscillator, you can see the active and the passive components like the transistors and the inductors. Again, in the inductors, you're going to have the substrate and the copper traces on the top. So because of these devices, you're going to mainly have three types of losses at high frequencies. One is the conductor loss, the dielectric loss, and the surface roughness loss. All these losses increases as a function of frequency. The dielectric and the surface roughness loss are completely the substrate properties. Also, if we look into from the perspective of packaging and integration, we need successful 2.5 or 3D integration with high density, low cost, and good coefficient of thermal expansion match between the CMOS silicon. So basically, we are looking for materials which can potentially satisfy all these requirements. If you look into the comparison chart here, we have three different types of substrates. One is the organic, silicon, and glass. If you look into the loss tangent or the dielectric loss of the material, the organic has the moderate loss at high frequencies, whereas the silicon has very high loss and glass has a relatively low loss compared to the other two substrates. Similarly, if we look into the roughness values, the organic both suffer from very high roughness values because in order to have good adhesion between the substrate and the copper clad, the surface of the substrate is usually roughened. And silicon and glass have the roughness in the order of few nanometers. Similarly, if we look into the packaging and integration, the integration density is low to medium for the organic, but it is very high for silicon and glass. Whereas the silicon has a very high packaging cost, same as like organic, but glass has a very low packaging cost compared to the other two substrates. From the reliability perspective also, glass has very high reliability compared to the other two. And also, if you look into the previous work, different devices like the antennas, filters, transmission lines are designed and fabricated on single glass substrate layers for millimeter wave communications. Whereas if we look into the multi-layer patch antenna stack-up, as you can see, we have different multi-layers with different feeding line architecture and through vias, which consists of an RF chip on the bottom and which is integrated also with the ball grid array packaging type. If you look closely into the interface between the Rogers board and the substrate, you can clearly see that there is a roughness between the interface layer. And also, in one of the previous work demonstrated, on a 28 GHz bandpass filter on Rogers 5880 substrate, you can clearly see that there is an additional 1 dB insertion loss at nearly 25 GHz due to the roughness effects of the substrate. Therefore, the roughness efforts try to hinder the performance of the device at high frequencies. But we can also see that there is only the multi-layer array antenna structures are usually demonstrated on PCB or organic boards which suffer from very high roughness values. So therefore, glass is suitable material for a millimeter wave devices and packaging, but 3D stack-up of glass for array antennas is not yet reported. So the goal of this work is to design and fabricate 28 GHz array antenna using through-fluid silica via technology, where we stack up two glass layers where the thickness of each layer is close to 300 micron. And the RF measurements are performed using two techniques. The first one is the mechanical clamping support, using the mechanical clamping support for copper to copper contact, and the second method is using cross-linked SU8 polymer as a bonding material between both the substrates. Coming to the design of 28 GHz antenna, in this slide you can see the design of a single patch antenna on two substrates. So you have the top substrate and the bottom substrate, which are separated with a ground plane in the middle. The ground is placed in the middle of both the substrates in order to reduce the coupling effects. So this design is designed on a fused silica of the dielectric constant close to 3.8 and a very low loss tangent value. The written loss of this architecture is shown here. You can see that the single antenna simulation from HFSS, the resonance frequency is the design structure with these dimensions is close to 28 GHz, and the bandwidth 10 dB bandwidth is equal to 0.89 GHz, and the simulated gain of single patch is close to 7.63 dBi. Based on the single patch performance, we tried to design the 4x4 array antenna. So you can see from the 4x4 array antenna architecture, you have all the 16 radiating elements on the top of the substrate. On the bottom of the substrate, you have the power dividing network, which is mainly used to divide and supply the power equally to all the radiating elements. So because of the implementation of this multi-layer architecture, the area occupied by this one is nearly 15% less compared to the single substrate layer. This is because as you have the feeding lines on a different substrate and the patches on the different substrate, the coupling effects are less, so that each patch can be placed close to one another. And also from the 2D gain plot, you can see that the simulated gain of this architecture at 28 GHz is close to 16.88 dB. So based on these simulation results, we try to fabricate the antennas on the glass substrate. Firstly, the glass vias are fabricated using LPKF's laser-induced deep etching technology, where in this process you have three main steps. Where first you use a single pulse modifications to closely pattern the vias on the glass substrate, and you try to merge these individual modifications or combine together and try to etch the glass. And finally, after the wet etching, you can clearly see the formed pattern on the glass substrate. So using this technology, different features can be easily fabricated on glass, as you can see it here, of different shapes. And also the other important thing that need to notice is, as you can see from the SEM images, the glass is free from any cracks and any defects. And also at the end of this process, the properties of the glass remains the same, as the internal stress formed inside the glass during this process is very less. Or once the vias are fabricated, the remaining steps of the fabrication are divided into two processes. So the first one is the ground plane fabrication. As you can see, where we have, once the vias are fabricated, we deposit 30 nanometers of tie followed by 500 nanometers of copper using sputtering technique. And for in the next step, we use dye film for the lithography and the patterning. And in order to have the metal deposition for thick metal layers, we use electroplating technique. Once the electroplating is performed, the dry film is removed, and finally the seed layers are removed on the bottom of the substrate and the ground plane is formed. Similarly, the top and the bottom feed line patterns are also fabricated in the same way. While the top and the bottom feed lines are patterned, the bottom ground or the top ground in case of the second substrate are covered with the protective layer in order to prevent the electroplating growth on the ground layer. So once the devices are fabricated, the total metal deposited during the electroplating process is measured. It is necessary to have a very smooth and a uniform metal deposition on the glass substrate, because since we are stacking two substrate, it is necessary to have a very smooth interface between both the layers. So the thickness of the metal deposited is close to 5.5 micron, and the surface roughness of this electroplated copper is measured using Bruker optical profilometer, and the measured average roughness is close to 50 nanometers. So these are the two fabricated feed lines and the patches on the two glass substrates. And as you can see, we used 1.85 millimeter SMA connector in order to measure the performance of these devices. So if you look closely into the vias on the ground plane, you can clearly see that there is a very good uniform conformal coating of the vias, and it is to be noted that the diameter of vias in the ground for the ground contacts is close to 400 micron, whereas the vias on the feeding lines is close to 200 micron. So the SEM image of the above structure is also shown here, and you can clearly see the deposited copper in the vias, and the thickness of the glass is close to the thickness that is run in the simulations, which is close to 300 micron. So RF measurement of this 3D integrated antenna is performed in two cases. As you can see, we have two substrates with the ground and the patterns for the top patch and the bottom feed lines. So these two are integrated together to form a glass stacker. In the first case, we use mechanical support in order to get that contact copper to copper contact between both the substrates. And also you can notice that there is a clear air gap between both the substrates. In case 2, we used cross-linked SU8 polymer as a bonding material for both the substrates, and in this case the SU8 is completely cross-linked using photolithographic technique. So using the mechanical support, the performance of the antenna is measured. As you can see that the measured resonance frequency of the antenna is close to 25 gigahertz using the mechanical support. And this shift in frequency is most likely due to the fabrication or assembly or measurement tolerances. And also it is important to note that there is a huge coupling loss in case of this structure, which is most likely due to a very less or a minute air gap between both the substrates. In the second case, when SU8 is used as the bonding material, the frequency is downshifted to 27 gigahertz, and also you can clearly show that the coupling losses are very less in this case compared to case 1. This slight shift in the frequency is most likely due to because the dielectric constant of air is close to 1, whereas the dielectric constant of SU8 is close to 2.65. So this slight increase in the change in the dielectric constant between the interface might have slightly shifted the resonance frequency to the lower frequency points. From the measurements, it can also be observed that the shift in the frequencies from the simulated results is between 3.5% to 5%, and which is under the tolerable limits. So measured resonance frequency matches very close with the simulation results. So from this comparison table, it can be observed that different antennas have been, from the references, you can see that the different antennas targeting 28 gigahertz have been designed, and the size of these antennas are typically 4 by 4, and different substrates like 4 layers and single layers are used for the designing of these structures. And from this work, you can see that the gain of these array antennas is close to the R demonstrated work of array antennas on the fused silica. And it is important to know that this work has the demonstrated work has the smallest footprint compared to the other existing architectures. It is also to be noted that the single substrate designs have relatively more footprint compared to the multi-layers. So this is because since on the single substrate you have the feeding lines and the patches, everything lying on the same layer. In order to reduce the coupling effects, the patches are usually made to spread, or the distance between the patches is slightly increased compared to the multi-layers. So therefore it is necessary to have a multi-layer architecture to have like a less footprint compared to single substrate layer, and also to have less coupling effects. So coming to the conclusion, from this work we can say that glass is potentially can be an ideal substrate for millimeter wave devices, packaging and integration. And this is the first demonstration of 3D integrated array antenna using through fused silica technology. And we try to measure the performance of the devices using mechanical clamping for direct copper to copper contact, and we also used cross-linked SU8 as a bonding material to measure the performance of the device. It is also important to note that the performance of this antenna matches close with the existing array antenna architectures, and also the footprint of this structure is minimum compared to the other devices. In the future work, we are trying to stack up more glass layers and simultaneously trying to reduce the thickness of each layer. And we are also trying to integrate the beamforming array technology using the materials like BST for the changing the radiation pattern. And also the gain and the efficiency of these structures can also be improved by using copper cobalt metaconductors instead of conventional copper, as copper cobalt metaconductors demonstrates less resistance at higher frequencies, especially at 28 gigahertz compared to conventional copper. The gain and the efficiency can be significantly increased. With this, the authors would like to thank the IMG and M&M lab members at University of Florida for technical help and support. Uh, a great thanks to LPKF Lasers Electronics for laser machining of the glass for via fabrication, and Koning Inc. for donating the glass samples. And all the fabrication is performed at Nanoscale Research Facility at the University of Florida. The the DuPont, we would like to acknowledge DuPont for the photoresist donation. And thank you. If you have any questions, please email to the following mail IDs given below. Thank you. Have a good day.